My name is Flora Vale. I'm a product engineer on the analysis and geoprocessing team. I focus primarily on data visualization to support spatial analysis, like charting and Pro, which we're going to explore quite a bit in today's session. And this is my colleague and friend, Dr. Lauren Bennett. She leads the spatial statistics team and manages and drives all the awesome development that's happening in the spatial stats and spatial pattern mining toolboxes in Pro. And our work intersects quite a bit because effective spatial analysis requires data visualization every step of the way. From exploring and getting to know your data so that you can really hone in on the appropriate questions to ask, to interpreting and making sense of your analysis results so that you can understand complex relationships in multiple dimensions, to communicating your findings effectively and honestly so that they can be useful, so that they can be used to actually make decisions and affect change. So let's back up a little bit. What is data visualization? Well, simply put, data visualization is the graphical representation of data. It's the use of symbols as metaphors to represent quantities and categories and context so that we can intuit proportions, trends, patterns, and comparisons. Here are some of the classics. You didn't think that you were going to make it through a data visualization talk at a mapping conference without seeing a Jon Snow cholera map, did you? I won't spend too long here, but the reason that you see a Jon Snow cholera map at every talk is because it was truly transformative. And every one of these examples, visualizing the data not only helped tell the story, but it actually made it possible to uncover things that would have been virtually impossible without visualizing the data. So Jon Snow, as most of us know, was able to identify a contaminated water tap and identify the cause of a cholera outbreak. Florence Nightingale was able to show that epidemic disease was causing more deaths of British soldiers in the Crimean War than actual battle wounds. Charles Menard elegantly put together many dimensions into one visualization detailing Napoleon's march, showing population, temperature, direction, time, all together in this classic visualization. And not nearly as historic, but almost as iconic, Hans Rosling wowed the world with his animated visualization of life expectancy over time in his 2006 TED Talk. So why do we visualize data? We visualize data to convert slow reasoning tasks into fast perception tasks, so that we can intuitively perceive relative differences instead of having to hold information in memory and perform mental calculations. The process of visual perception is pre-attentive, which means that it happens automatically with virtually no effort, in contrast to attentive processing, which requires conscious effort and calculation. So, for example, if I were to ask you to identify the largest value on this slide, it would be a pretty tedious task. You'd have to do a lot of mental sorting and hold a lot of things in memory. But if I showed you these values as bars in a chart, you can immediately tell which value is the largest, because now we're using length as a visual encoding to represent these values. So we're using pre-attentive processing, and the information is immediately evident. In 1967, a French cartographer named Jacques Bertin published what has now become a fundamental reference in data visualization, titled Semiology of Graphics. And in this book, he describes visual variables and how they can be used to communicate effectively. More work has been done on this since, but these visual variables are still the foundation of most data visualizations. So we have position, size, shape, value, hue, orientation, and texture. So in this visualization, we're using position to perceive the relative length of these bars. And many researchers agree that position is actually the visual variable that we are best at perceiving. Of course, we could also use size, hue, orientation, or any of the other visual variables to make this text stand out. But not all visual variables are appropriate for every data type. Noah Alinsky, who was a thought leader in the data visualization space, put together this great table detailing best practices for using visual encodings. So for example, size is a great way to represent quantitative and ordinal data, but not appropriate for categorical data. Color can be a great way to visualize categorical data, but only when there are few categories. All of this is important to keep in mind because not all data visualizations are created equally. Understanding how our eyes and brains perceive visual variables is key to effectively communicating through data visualizations. So let's go ahead and get this one out of the way. The pie chart, though beloved by many, is not the most effective way to visualize proportions. Understanding a pie chart requires us to visually compare angles, which we're not really that great at doing. Looking at these three charts, it's not immediately evident which slices are largest in each pie. But if we look at these as bar charts instead, the information is immediately obvious. We don't have to use any attentive processing. We don't have to figure anything out. We just get it. Really, we want to get the most amount of information in the least amount of time with the least amount of effort. So with the bar charts, we just get it. No need to figure it out. So what's worse than a pie chart? A 3D pie chart. There are whole corners of the internet dedicated to criticizing the misleading visualizations used in Apple keynotes. Notice how the 19.5% Apple market share appears larger than the 21.2% slice in the top corner. And the donut chart. The donut chart may be a cooler or a prettier version of the pie chart, but they're even harder to decipher because now we've removed those angles that we were comparing before, and we're left to just compare arc lengths that don't have a common origin. So they're more difficult to understand, and I would recommend most of the time donut charts are not going to be appropriate. And then, of course, the 3D donut chart. Please don't do that. Look, all of these rules have exceptions. I'm not telling you that it's never okay to make a pie chart. Sometimes they can be useful. But I'm going to go ahead and step out on a limb and say that you're never allowed to use a 3D donut chart. With very few exceptions, 3D charts are highly discouraged. While bar charts are one of the most dependable and easy to read visualizations, when they're drawn in 3D, they become hard to decipher. So in this chart, it's really hard to tell which edge I'm supposed to be comparing to the axis on the top and on the bottom. And what's hiding behind that bar? There's no way to tell. So this could have just as easily been drawn in 2D with using much less chart junk, as Edward Tufte calls it. So putting these in 3D not only didn't add any value, but it actually distracted us and made it more difficult for us to clearly see this data. Another way to obscure the trusty bar chart is to remove its origin. Bar charts must always include 0. And that's because we are using these bar lengths to perceive relative proportions. So notice how in this chart on the left, the preoperative value seems like it's less than half of the postoperative value. While in the correct chart on the right, which has a zero origin, we can see that difference is much less severe. The next chart faux pas is using lines to connect arbitrary categories. So with few exceptions, lines should be used only to visualize change over a continuous variable, like time or distance. So using lines to connect discrete values like states doesn't really make sense. Bars, again, would have been a lot more appropriate for this visualization. Okay, here's our last chart crime of the day. There's this great website called WTF Viz that I really enjoy, where people submit misleading, incorrect, or otherwise just terrible visualizations. And this one is a great example. So while line charts are a great way to show change over time, this one is doing a terrible job. So we're looking at changes in homicide cases over time. And each one of these data points represents one full year of data, except for the last two. The second to last data point represents about 6 months of data, January through June. And then the very last point only looks at July 1st to August 3rd. So of course that line is going to be sloping down. Comparing a whole year's worth of crime to 1 month worth of crime, we would hope that line would be sloping down.
It's actually not sloping as much as it should be, really.
Yeah. It's really hard to believe that this misleading visualization was unintentional. So now that we've had a little crash course in some of the do's and don'ts of data visualization, let's take a look at how we can effectively use data visualization throughout our spatial analysis workflows. So in addition to visualizing our data in 2D maps and 3D scenes, we can also use charts throughout the spatial analysis process to visualize distributions in frequency, category comparisons, relationships and correlations, and change over time or distance. So most of us are familiar with the importance of visualizing spatial distributions, but visualizing distributions in data space can be equally as important. Histograms are a great way to check if our data is normally distributed. A lot of analyses require normally distributed data. Also, when data is not normally distributed, we can't really trust some of these summary statistics like a mean, for example. So with normally distributed data, the mean falls in the middle of this bell curve because it's most representative. It's also the mode. But when data is not normally distributed, the mean is actually not representative of the data set. There's this example that a favorite comedian of mine, Bo Burnham, says in one of his specials that the average person has one fallopian tube. So there definitely are some people that have one, but most people either have 0 or 2. But if I just give you that average value, you're going to think that 1 represents the population, when in fact we have a bimodal distribution and the mean is not representative of the whole. So it's important to visualize the distribution of our data, and we also have box plots, which are a great way of visualizing and comparing distributions across different categories. We can use bar charts to compare amounts across categorical data. We also can use stacked bars to look at part-to-whole relationships, since I'm not giving you pie charts. And we can use scatter plots to visualize the relationship between numeric attributes and to calculate linear trends. And we can visualize trends and cycles over time using line charts or data clocks. So we're at the Esri conference, and I think it's safe to say that we all love maps. But sometimes a map alone is not the best option. And state maps are a great example of that. Now, I'm never going to tell you not to make a state map, but I think that state maps can usually benefit from a companion chart. In the case of state maps, mapping our data is really valuable when the location of the values matter, right? With states, it's not really about where the states are. We're actually just comparing categories. State sizes and locations are really a lot more political than they are a spatial phenomena. States being next to each other does not necessarily mean that they're related. So we're really not, location is not the most important attribute here. And states are very unevenly sized and shaped. So some tiny states get lost. And with a choropleth map like this, we can tell the states with the darkest color, but of those states, we can't tell which one has the highest value. So creating a bar chart helps us interpret those values. And we can quickly see here that I think Nevada has the tallest bar. And even better, if we were to sort this bar chart, now the relative differences are even more apparent. Another example of when visualizing our data becomes really important is with relationships. So this is a classic example called Anscombe's quartet. And these 4 data sets have the exact same mean, median, standard deviation, and R-squared. So if we were just to get those summary variables, we might think that these are all very similar or exactly the same. When in fact, if we visualize these on a scatter plot, they're all quite different. Some are kind of linear, some have really crazy outliers, some are a little bit curvy. So visualizing this data is kind of the only way to tell that these 4 different data sets, while very similar in summary statistics, are actually quite different in shape. Another example when a map alone might not be the best option is when looking at time. So animating these points on and off, showing different time periods, is not really all that useful. Creating a line chart now shows us that pattern over the time so we can understand better what's going on in this temporal data set. Another neat way to look at time using line charts is to split up something like time of day and day of week. So here I'm looking at fatal car accidents over several years. And I split this up looking at hour of day across the x-axis and then the number of crashes along the y-axis. And each line represents 1 day of the week. So the purple lines are the weekend and the blue lines are the weekdays. So we can see that the most dangerous time to be on the road is 2 a.m. on a weekend. While during the weekdays, we see that kind of rush hour hump in the morning and then in the evening. So something else that wouldn't really be easy to visualize just using a map. So let's take a look at some of these charts in action. I'm going to show you a little demo of exploring your data in Pro using charts. So let's start here. I downloaded this data set from cms.gov detailing the health of, sorry about that, guys. Sometimes when switching from slides to demo, let's duplicate these.
Make sure you accept changes.
Yes, thank you. Learn my lesson.
Do it all the time.
Okay, so I got this data set from cms.gov detailing the health of Medicare beneficiaries in each county. And looking at this table, I can't really make any sense of anything. So the first thing I do, of course, is put this data on a map. And here I'm looking at the average HCC score, which is an index used to measure the health of the population. So the higher the HCC score, the less healthy the population. The areas in red, the least healthy, areas in green, the most healthy. So now I already have a much better understanding of this data set. I see the spatial distribution. I'm starting to see some visual clusters, but I want to explore this a little bit more. So the first thing I'm going to do is create a histogram. and see if the HCC scores are normally distributed. Oops. So looking at average HCC score, we do see a nice bell curve. We can also show a normal distribution overlay here. And I can add the mean, median, and standard deviation lines to this chart. And it does look very nicely normal. If I look at a different attribute here, like number of beneficiaries, now we're going to see that it's very skewed. And that's kind of to be expected when we look at things like population, right? Most places have a smaller number, and then some outlier places, if I select here, we can see that, of course, it's LA, have a very high population. And there are some ways that we can deal with skewed data like this by using a transformation. So if I apply a logarithmic transformation to this data, then we see that it becomes normally distributed. So oftentimes when running analyses, when we're looking for linear relationships, but we're not able to find one, if we transform our data, we might be able to figure out how to best use it for our modeling purposes. So I'm also going to go back to our HCC score here. And now I want to look at another one of these health characteristics, like the percent of diabetes in the population. So if I put these histograms side by side, I'm going to select the tail in the diabetes chart, looking at the areas with the most diabetes, to see if it kind of falls in the same part of the chart with the least healthy population. And actually, while it kind of selects on this tail, there's more kind of happening in the middle. So now I'm going to use a scatter plot to see if there's actually any relationship between the health of the population and the percent of diabetes. So I'll create a scatter plot and look at these two variables. Percent diabetes. I'll dock this over here so we can see everything at the same time. And so now we see that we do kind of have this positive correlation. We get an R-squared value of 0.61. And you can see that the colors of the counties in the map are actually maintained in the scatter plot. So the colors correspond to the HCC score. And that's already what I'm using on the x-axis. So if I change that to a different variable, like maybe high cholesterol, I can now see the relationship between high cholesterol, diabetes, and include HCC score as a third variable through the color of the points in the chart. I could also summarize this by state with a bar chart. So instead of having to create a summary table adding up every county in each state, I can just use state as the category for my bar chart and then look at something like the percent of diabetes and look at the average and maybe sort that descending, select the top few, and we see the states here that have the highest rate of diabetes. So that's just some simple data exploration of county data. Next, let's take a look at some exploration of some ocean data. So here I have some water quality readings in the ocean over depth. So we're looking at dissolved oxygen. And so we have many dimensions here. We have the location in both X, Y, but also in Z, depth of the reading. We have the year and the month that the record was taken, and we have the level of dissolved oxygen. So what I've done is I've set up a range slider here to look month to month and have the chart looking at the annual dissolved oxygen. But we're only looking at 1 month at a time because we expect some sort of seasonal pattern. So I'm only interested in looking at how the years have changed for each month. So looking at here, let's say July, we can see the pattern of Julys over year, and we can also see how the oxygen changes over depth. Looking at August, we'll see that the charts will update according to the range slider. Charts also will respect time sliders if you want to explore your data temporally in that way. And another thing that I wanted to show you here with the ocean data was something that I found looking at temperature. So I had this temperature data set, and I wanted it to kind of do the same thing and check to see if temperatures in certain months had been increasing year to year. So I created a bar chart of temperature over year, and one of month. So I was going through and selecting other way around. I was going through and selecting each month and seeing how that's changed year to year. But then I came across this bar, and looking at this mean temperature, I was kind of worried that maybe these were data errors. So I selected this bar and took a look at our attribute table and found that these temperature readings were like 64, 63 degrees Celsius, which is like something like 140 degrees Fahrenheit. So by visualizing this data, I was able to find those records that were entered incorrectly and then go through and convert those to Celsius. So visualizing your data is also a good way to make sure that your data is healthy. Sometimes outliers are true outliers, and sometimes they're just data mistakes. And the last thing I'll show you here in data exploration is looking at time. So here I have some violent crimes in Chicago, and I want to explore if they've been changing over time. So I can create a line chart, and the line chart is actually going to aggregate a date field for me based on the temporal extent of my data. So in this case, it's going to aggregate into 2-week intervals. So each one of these data points represents 2 weeks. They're all even, no misleading here. And we can see that kind of seasonal trend, ups and downs over time. I could also change this from 2 weeks to maybe, let's say, 1 month, and see how those have been changing month to month. I could maybe split this data up to compare different lines. So let's take a look at these by the type of crime and how those have been changing month to month. So now we're going to get one line for each of the primary crime types once my chart loads. Here we go. So we can see that in red we have the highest number of robberies, and in the darker blue, battery, etc. So we can kind of see multiple categories changing over time in one chart. And the last thing I'll show you here is the data clock, which is new at the 2.2 release. And the data clock is a great way of visualizing both trends and seasonality. So looking at the crimes over years and months, every ring in the data clock is 1 year, the most recent year on the outside, and then every one of these wedges is 1 month. So we can see here that these summer months have had the most crime, and those crimes have actually been decreasing year to year. So in May, we have the dark blue in the earlier years and the lighter blue in the more recent years. And I could also split this up by maybe weeks instead of months, or even look at days over this chart. So an interesting way, and also, of course, these are all selectable, and every time you make a chart, you can find it in the List by Charts tab over here. So I can open that line chart again that I created and compare how that looks to my data clock. So we've kind of looked at some ways of exploring your data and doing some visual analysis as you prepare for the real kind of heavy-duty analysis process. So I'm going to jump back into the slides really quickly. And all right, just worked this time. So we talked about when a map alone wasn't the best option, but we also need to talk about when we need more than just a map. So we need a map, but we need more than just a map because often our analyses involve multiple dimensions and complex relationships. And so in order to understand the results of these analyses, we're going to have to do a lot of different visualization types to get around the whole story. If you've ever seen Lauren or me do a talk, you've probably heard us talk about the subjectivity of maps. So we're looking at this data set, again, of crimes in Chicago, and looking at these points by themselves is not really telling us much, so we might do something like create a heat map. And a heat map definitely helps us start to understand the spatial distribution of these crimes. But as you can see here by the legends, these maps are actually the same density surface, just symbolized in different ways. So you have to be above, what is it, something like 1500 to be the darkest red in the chart on the right, and above, 1500 above 900 in the chart on the left. So the point being here that we have a lot of decisions that we make in how we visualize data, and we have a lot of responsibility. Just like with the charts, we can make misleading charts, we can also make misleading maps. And one way to get around that is to start to perform analysis. So something like a hotspot analysis helps us minimize the subjectivity of a visualization like this. But analysis not only helps us minimize these subjectivities, but it also requires some sophisticated data visualization, especially when we're including multiple dimensions, like in this example, time. So looking at a hotspot analysis over time is going to require the aid of a 2D map, a 3D map, and a long, complicated legend that we'll talk about in a little bit.
Rude.
Or a long, very useful legend.
Thank you.
Or when we're looking at multiple variables, like a multivariate analysis. We can use the multivariate clustering tools to find clusters in these multiple variables, but it's impossible to understand what the different clusters mean without a companion visualization. So let's take a look at some of these more complex analysis types and their need for data visualizations with some demos from Lauren.
Okay. All right, so we're going to go through a couple of different examples of places where we've been collaborating with Flora to think about how we visualize the results of our analysis. It's very easy as analysts for us to get really caught up in the awesome algorithms that we're using. At least for me, I get really excited. And then we look at the results and it's like, I don't know what this is telling me. I know I used a really awesome algorithm though, and as useful as that is, if we can't interpret the results and then communicate those results, then our analysis isn't useful, right? I mean, we can do the best analysis that has ever been done in the whole history of humanity. And if nobody can understand what we did and nobody uses it to make a decision, it's useless, right? So that really does become a really important part of our job. So this is a really good example of that. So we developed a new tool called density-based clustering. Basically, it looks for natural clusters in our spatial data and finds them and distinguishes between them on the map. Now, the way that density-based clustering works, you don't tell it how many clusters you're going to find. It just finds the clusters in your data. Now, what that means is that sometimes you've got hundreds or even thousands of clusters in your data. And when we first were done with our prototyping of the tool and we were doing some preliminary testing, we were just using a unique value color renderer. And it turns out there aren't really 1,000 unique colors that are distinguishable by the human eye. So the tool would run and you'd look at the TOC and you'd just scroll through thousands of different colors, right? And a lot of them look like the same color. Like the RGB value changed by 1. So it's technically a unique color, but they're both light blue. And what happens is they end up next to each other at some point. It's inevitable. Randomly, two clusters with very similar colors are symbolized right next to each other, and all of a sudden, I can't tell the difference between clusters, which was, of course, the whole point of running the tool in the first place. So we were absolutely racking our brain, how do we deal with this? So I went and I talked to Craig Williams on our mapping team, and I said, okay, we've got this problem. It's very unique. No one's ever faced this problem before. He said, that sounds a lot like this thing called the four-color theorem. I have no idea what you're talking about. Turns out, wasn't a unique problem. Many have faced it before. The most common example of it is in creation of atlases. So in an atlas, you're creating a map of countries or states or regions, and of course, you don't want to use a unique color for every country in the world. You just want to make sure that countries near each other don't have the same color. So there's this thing called the four-color theorem that goes through and makes sure that countries near each other don't have the same color right next to each other. So we started playing around with it. We realized pretty quickly that 4 colors wasn't going to be enough for us because countries generally have some sort of, they're polygons, if nothing else. And so that's a different challenge. We're talking about points that can have very strange shapes. These clusters, as you can see, can follow networks. And if you have, let's say, a big blob of color in the middle, and you only had 4 available colors, we wouldn't really have enough to kind of go around it. So we upped it to 8, and we return the results of the analysis in a way so that you can see it's not that these red clusters are the same cluster. They're unique clusters. They're separated by other colors, right? And in the legend, we tell you that you've got 8 clusters that are displayed in red. And so it's a way of starting to understand how the visualization's working. So to me, this is a really good example of the importance of thinking about visualization, even just from an interpretation standpoint. Although in this case, it's both interpretation and communication. Another way that we use visualizations for the density-based clustering tool is actually less about interpretation and almost more about understanding the method and understanding the algorithm and how it works. So a lot of our tools actually, a lot of the spatial stats tools create charts when you run them. You might not know about it, although we're working on that to move charts up further in the TOC. But for right now, in the TOC, there's this option to go to list by charts. So if I go to list by charts, I can see these charts that were automatically created when I ran the tool. You don't have to create them. We just create them for you. And one of them is this reachability chart. So what density-based clustering actually does under the hood is it starts at a feature. And it looks for that feature's next closest neighbor. And it measures that distance. And then it finds that feature's closest neighbor. And it goes through looking at all the closest neighbors without ever going backwards. It never repeats. It never returns to a point that's already been visited. So it goes through, it finds all those distances between clusters. And what happens is, when it's in a cluster, you see a lot of small distances. Then it's out of that cluster and it jumps to a piece of noise or to another cluster. So there's a big distance between 2 clusters. Then it's in a cluster again and it's small distances. And then it jumps to another cluster, big distance, small distances. And so that's really represented here in this reachability plot. So the reachability plot, the valleys in the plot represent those clusters, and the peaks represent noise, right? We can see the small distances are the clusters, and the big distances are features that aren't part of clusters or jumps between clusters. So for one thing, just seeing the reachability plot and starting to understand how it's being used to differentiate between clusters is very useful for us as analysts. A lot of times being able to look at charts is a great way for us to really deeply understand the way that the tools that we're using work so that we can explain it. I know that we've all faced, we've done this really awesome analysis. We're really excited about it. We show it to someone. They're like, okay, that's cool. Can you explain this to me? And we're like, yes. This kind of approach where we dig into those results and we really get a deep understanding of it is a really great way for us to be able to feel confident explaining it. In this case, it's also very useful for us in fine-tuning it. So the way that optics works, which is the method that creates the reachability plot when you run density-based clustering, is that there's a parameter called cluster sensitivity. And essentially what that's a parameter that's determining how sensitive do you want our clustering to be to peaks. So if you have very low cluster sensitivity, the peaks have to be really high in order for it to say this is one cluster, this is another cluster. So you can imagine if I made, in this case I used a cluster sensitivity of 50, it goes from 1 to 100. If I used a cluster sensitivity of 2 or 3, it would probably find only a few clusters, maybe even just 2. It would probably group everything on the left-hand side of my chart here as one cluster, because those are all very small peaks, and it might just find this one blue cluster here over on the right. I might alternatively say, you know what, 50 wasn't good enough. I think this blue, light blue cluster here is too big. And I want to find little differences in that cluster. I want some of those, albeit very small peaks, to start differentiating between even smaller clusters. And so I could up that cluster sensitivity to like 75 and see if it's doing a good job. And so I can also use the chart to help me fine tune my analysis. So it plays a couple of different roles in this case. All right, so that's density-based clustering. Another really good example of where charts are and visualization is absolutely critical is this one. This is the results of our spatially constrained multivariate clustering tool. So this is a tool where you give it a bunch of different variables. This is oceans data. And we've got a bunch of different attributes of these sample points in these various areas of oceans all over the world. And what we wanted to do was find regions that are similar in terms of these various attributes, right? So we ran spatially constrained multivariate clustering using 6 variables, created 6 clusters, and we get this result. I'm sure you'd all agree this is a very useful result. I've learned a lot about my attributes and all of the different characteristics. I have a yellow group, I have the blue group, a red group. By itself, this is not very useful, right? We know where the groups are, but I can't say anything about them, and I'm not going to go into a meeting talking about the yellow group, right? So a absolutely critical part of this is how do we tell somebody about these groups? So when we first started working on this tool, which was actually quite a while ago, we were thinking about this, where we'd have a summary for each variable. So in this case, this is a different, luckily you will never see this anymore. So this is an old PDF report that we created. But let's say the variable was about reading scores. And it says that the average for all of the reading scores was 90, but the blue group was 91, so it's a little above average. And the red group was 88, a little below. And the green was a little above also. It looks like it was a little above 1. Okay, so this is very interpretable. This follows all the rules that Flora just went through, right?
A lot of attentive processing required there.
So luckily, we also, myself and my colleague Lauren Griffin, we signed up for this course that was happening in LA that Edward Tufte was teaching. He's a very famous researcher in this area of visualization. And we went to the workshop, and one of the things that he talked about were spark lines, which was this idea that we might include charts even in something like a table, where right inside the table we boiled down, essentially this simple graphic actually depicts all of the data that's in all of these numbers, right? But even this, it turns out, was too much. So the way that it works now, because we did all this, and at the end of it, we also came up with this brilliant idea that we'd stack these box plots together, and we'd put all that information for each variable for every group together. And we put all of our ideas in that PDF, but I literally have never looked at anything except the box, this one graphic, right? Because it has everything that all of those other pages of numbers have. So luckily now in Pro 2.0, in Pro, with our release of the new spatially constrained multivariate clustering tool, we can take advantage of the box plots that are part of Pro. So here we'll open up our box plots that get created just when you run the tool. It creates a box plot. And we can take a look at what each of those ocean areas are. So for instance, the yellow group stands out as being really interesting, where it's got very low salinity compared to the average. So each of those boxes represents the global average for all of that oceans data. And then the lines represent where those groups fall in relation to that average, right? So we can see that what the tool was able to do was pick up on those landlocked oceans, essentially, that have a very different signature, particularly based on salinity. Or we can see, for instance, the orange oceans down here that have high levels of nitrate and silicate. So we can see kind of what the characteristics are of each of these groups that get created. This was an analysis done by one of my colleagues, and he was trying to do some modeling, and he just started exploring his data. And the reason he ended up running grouping in the first place was because one of the relationships he was trying to model, he was trying to create a model, and he noticed that the relationship between temperature and salinity was very complicated, and that not all of the ocean samples were following the general pattern. And he saw, when he looked at this, there was this clear area where the relationship, right, between temperature and salinity doesn't kind of follow the natural pattern. And that is exactly what the grouping analysis, the spatially constrained multivariate clustering tool found, right? It found that those same features to be part of this distinct group. So the last example I want to look at is looking at space and time. So this is another really good example where we went into it, I don't want to say blind, but we weren't totally sure about all the challenges we were going to face when we started to visualize the results of our analysis. So this is looking at power outage data in Houston, and it is what are called momentary power outages. So it's the power flips off for just a second and it goes back on. It often is related to like a tree branch rubbing up against a power line, something like that. But repeated momentary outages in the same location can be a good indicator that, let's say, tree trimming needs to happen, for instance, or something's coming. So it was actually about 50 million points in this area. They happen relatively frequently. You don't even notice them. And, well, first of all, you can imagine what a map of 50 million points in this area would look like. Super useless. I get asked all the time, you know, we work on these space-time tools and we work on some problems that really are most appropriate for big data. And people are like, yeah, but can you put my billion points on the map? I'm like, why do you want to put a billion points on a map? That will not be useful. Like, it is a guarantee that it will not be useful. So we can do a lot more than that. And one of the things that we can do is use some of these space-time pattern mining tools that are part of the spatial stats toolbox. And one of the things that we do in that process of this spatiotemporal analysis is we create what we call a space-time cube, which sounds very fancy, which is a benefit. You get to tell your friends you're making space-time cubes, press them all. But actually, it's very simple. We're just aggregating data in space and time. We're creating a grid in space and a grid in time, and we count up how many things happened in each space at different intervals of time. It's very simple. And essentially, you can think of that cube looking something like this, right? So we have, for any given point in time at any given location, we know how many outages happened at that time period in that location. So one of the first things you'll notice is we're using 3D to illustrate time. The further away from the ground something is, the more recently it happened in time. So the most recent slice is at the top, the one farthest away in time is at the bottom. So that was one of the first things we started doing, is kind of flipping 3D on its head and using it for a different purpose. Kind of pushing the bounds of what we were previously doing with 3D. Certainly for us as you know, I focus on spatial statistics. I don't do a lot of 3D. 3D to me has always been about buildings and cities and realistic cities, and that stuff's super cool. And I'm really glad other people work on it. It just doesn't get me super excited. But when we started working on time, it was like, wow, thank goodness that we have all of these 3D tools, because otherwise we really can't visualize this data. Because the alternative would have been maybe flashing a bunch of data on the map or showing slice after slice after slice. It's just way too much for us to try to interpret visually with that kind of animations or sliding. So beyond just aggregating into a cube and looking at a thematic map, which are wrought with a lot of the problems that Flora mentioned about the subjectivity of maps, right? I chose a classification method here. I've got dark purple, I've got light purple, but I can tell a lot of different stories using just a simple thematic map. It's not just heat maps that lie, right? I can go in here and change this classification method and make it look like there's a lot more power outages if I want to. So we wanted to do more, and one of the things that we do is run a hotspot analysis. And so I'll change the visualization to look at that 3D hotspot analysis result. We'll point you to resources where if you're interested in learning specifically about this kind of analysis, we have a lot more resources that you can use to do that. Essentially, what we have here is the result of that 3D hotspot analysis. We've got clusters of high values, clusters of lots of outages in red, and clusters of low numbers of outages in blue. So in red, we've got places where we have more outages than we would expect based on random clustering together. And in blue, where we've got less outages than we would expect clustering together based on random. Randomly, we'd expect to see kind of a salt and pepper pattern, but that's not what we're seeing. So it's great. We've minimized the subjectivity. We were really excited about this result. But as soon as I saw this result for the first time, and it took us a long time to get here, we had to build a whole new data structure, and then we had to work on the tool to do the 3D space-time hotspot analysis, and then I got this result. And I was a little overwhelmed because that's a lot of data for me to make sense of, right? Here we're looking at it in a real-world space where each bin represents its real location on the ground. But if I changed it to screen space, one of the challenges, it looks cool that way, but I can't see inside the cube that way. But if I could just see inside the cube, that would solve all of my problems, right? Now I know everything there is to know. Okay, so we realized pretty quickly this was not going to be enough. So that visualization that you're seeing kind of peek through at the bottom there is what we came up with. And that was what Flora so affectionately referred to as our categories. So these are the categories we came up with. There are 17 of them. It's really just 8 categories. There's 8 hot and 8 cold. They're the same, just some are hot and some are cold. So it's 8 categories. And they're all really useful as an analyst, right? So for instance, I have what we call This data set has a lot of what we call oscillating hotspots, where at some point it's been hot and at some point it's been cold. I'm not used to seeing a map actually with so much oscillating hotspots and cold spots because usually if I look at like crime, it doesn't oscillate between hot and cold. If a place is a hotspot of crime, it's a hotspot of crime. Maybe it gets to random, but to go all the way to cold, very unusual. So my initial reaction was doesn't seem right. But the idea here is that we're essentially boiling down. I think about it like we're boiling down that whole cube. We're smushing it down and giving you one way of interpreting that cube based on the trend at each location over time. So for instance, if we turn back on the 3D, we can see what it means to be an oscillating hotspot. We can see that in those oscillating hotspots have been both, they've been nothing, they've been hot, nothing hot, cold, hot. They finished hot. What makes them an oscillating hotspot is at the end, in the most recent time period, they're hot. There's a big focus in this tool on what's most recent because a lot of the times we care most about what's most recent, right? Similarly, we have a category called a new hotspot. So the new hotspot, if we take a look at just those new hotspots, we can see cold, nothing, cold, and only for the first time ever in the most recent time period was it hot. It's never been hot before. It's almost like an alert. I want to know about that place. What's going on there, right? So we learn a lot. I did find out when I was exploring this that through some charts that the pattern actually makes a lot of sense. The fact that we're seeing oscillating makes a lot of sense because this is a very seasonal thing. We see more power outages in stormy months. So when I showed this, I did this analysis working with the customer. I was like, I'm a little worried about these oscillating hotspots. They're like, oh, that makes perfect sense. This is a seasonal thing. And we see the highs here and the lows there. I was like, well, this is why we work together, subject matter experts. people who know how to use the tools. It's a symbiotic relationship. So that combination, I think what's important here is this idea that it wasn't enough to look at all that data in 3D, but it's also still not enough just to look at it in 2D in those categories that we created, right? It's that combination where I look at it in 2D, I see which areas I want to focus on, I zoom in there, I learn more by looking at the 3D. I can use the 2D to essentially narrow down those places I want to investigate further in the 3D. So I'm not looking at hundreds of thousands of bins, but now I'm just looking at individual locations I'm most interested in, like I did here with the new. Now, all that said, as much as these categories are incredibly useful to us as analysts, I mean, I would frankly like to have more categories. Give me all the categories. I want to know exactly what's going on here. But I'm an analyst. I'm not the decision maker. And I'm the one digging in deep into this analysis, right? So we had been working on this for a while. It's actually the topic of my dissertation, so I'm probably extra sensitive to this work. And I was presenting it to in one of our directors' meetings where we kind of show the directors of the company what we've been working on. And Jack sits like right across from you. You're presenting at the very end. He's very excited. He's like, but there's too many categories. It's like, no, there's the perfect amount of categories. There's not enough categories. What are you talking about? He has since changed his mind. He's gotten to know the tool, and he's a very analytical person, so he also wants to dig in. But as a decision maker who's being told a story, who's being communicated to, he was right. It's too many categories. This isn't how I'm going to communicate my story to a decision maker. It's how I'm going to analyze it. It's how I'm going to interpret it. It's how I'm going to figure out what's the story. And then I tell the story. And my job as an analyst, as a storyteller, is critical. So one example of this is we were looking at some sales data with a customer, and the default output is reds are hot and colds are blue. So if you're looking at sales data, your hotspots are going to be high sales. They're like the places doing the best, and we're making them bright red. It is absolutely not how a decision maker in a sales organization is going to think about their data. Those are not the hotspots. They might want them to be green. Those are the places that are doing really well, but red generally is bad. So you're not going to make really good areas red. So immediately we just started playing around. We condensed some colors together because, they didn't care about the difference between intensifying, persistent, or diminishing. Since all three of those categories mean that it's been significant at least 90% of the time, they said, we don't care about the difference between them. And there's nothing magical about these categories. We gave them to you to help you interpret them. But if you don't care about the difference between diminishing, a persistent, or intensifying, lump them together. Consistently hot, great. There's nothing inherently right about the categories. They're just helping you interpret them. So we lumped things together. We changed the color ramp. Another good example of that is some work done by Global Forest Watch. These are the folks at World Resources Institute. We worked with them and their partner Blue Raster, and we did some analysis of forest loss using emerging hotspot analysis. And they wanted to tell a story not to analysts, but to policymakers, like really far away from analysts. Right? And so they started telling a story. And I think they did a beautiful job. And it's clear they're using our tool, right? They created a visualization where in 3D, someone who wants to dig in and really get a sense for these patterns can. They also showed the results of that 2D map, except it doesn't look anything like our results. They told the story the way that they needed to. They brought categories together, they changed colors around, and now they told a story that is very intelligible to a person who is not an analyst, right? So I think this is a really important story part of the puzzle. When story maps came out, I was like, these are beautiful, they're really cool, but I do analysis. And very quickly I realized that actually this is going to be one of the most important tools in my tool set. Because it all comes back to this idea that it doesn't matter how great my analysis, if nobody uses it, if I can't communicate it, then it's irrelevant. And one of our biggest challenges is, at the end of the day, decision makers have a lot of information products that they're using to make important decisions. And I know most of you are making information products, not for yourself, but for others, right? At the end of the day, our information products are competing with all those other information products. And some of them are really sexy and totally bogus. So we have to win the competition. Ours have to be sexier and also better. It's not enough for us to say, but our science is right. That's a cop-out. Make it also a more compelling visualization. Do both, right? Do the better science and make it beautiful and intelligible to somebody. So hopefully we've given you some of the tools that are available to you and a sense of what's possible and some of the pitfalls.
Yeah, so that covers it. Thank you guys for coming. If you want to learn more about those spatial stats methods that we talked about, you can go to esriurl.com/spatialstats and watch some of our other workshops. I'll also quickly plug our workshops this afternoon. We're teaching regression analysis twice this afternoon, and it's going to cover that new forest-based regression and classification tool. And also, if you guys wouldn't mind, please fill out a course survey. They're on the app now, and so we get far fewer than we'd like. We used to hand out paper surveys, and we'd get a ton back, and now we only get a handful. But we really do appreciate your feedback. We use it to improve our workshops. We use it to justify which workshops we teach, which rooms we get to teach them in, etc. So we really appreciate your feedback. Thank you.
Thank you, guys.